So what is this propagation delay? The propagation delay is the average transition time of the signal from input to the output. Average transition time of the signal from input to output. And it actually defines the operating speed of the IC. Because how fast we are getting the output whenever we give to the input. So it actually describes or defines the operating speed of the IC. And it is measured in nanoseconds. So for example, if we have a NOT gate, a simple inverter, a simple gate, NOT gate. So here we give our input signal and here we get our output signal. But we will not give our output signal instantaneously. When you give some input signal, we will get output signal after a little bit time. That is the propagation delay. For example, so this is my input signal. We are giving the input signal here. So this is logic high, this is logic low, this one is logic low. We give this signal to our inverter circuit, and the inverter circuit will give output output signal. That means the gate will take some time to respond the input signal, and then it will process the signal. The time that will take for response, we can take some minimum time that is known as the threshold voltage. Usually we can think at the 50%, at the 50% of the signal. So that means the input signal is going to high to low. There is a transition from high to low, and again from low to high. This is the input signal, right? We give our signals. So, and it will take some time to response. And here, this is the threshold voltage for the output presentation. So if we extend this one, this is the 50%, and this is the 50%. So this is my input signal, this is my output signal. So this is from high to low, and this is from low to high. Sorry, I draw both the same way, sorry.
It should be opposite.
Should be opposite. Because it's an inverter circuit. I'm sorry. So this is output signal. This is from low to high. So we give our input signal here to the inverter circuit. It will respond after some time. So this is that time, this is the threshold voltage. Usually we can consider as 50% time. At that time it will respond. Then once it will respond, it will go some take time to respond to give the output. So when we give 0, it will give 1. We are giving, or if you give high, it will give you low. So we have two different transition time differences. One is known as TP, HL, and TP, LH. TP, LH, and this one is TP, HL. TP, LH means transition time or propagation time from low to high. So from low to high. And this is the propagation delay from high to TPHL and TPLH. So this delay at the time output side as a response of the logical operation. So this is the delay at the output side. We are not taking the delay at the input side, we are taking the output side. So this is the delay at the output side as a response of the logical information. So as I mentioned, it is an average transition time of the signal from output to the input. And it actually defines the speed of the IC. And it is always given in nanosecond.
Is this TPHL and TPHL and TPLH
LH.
same?
So propagation, yeah, it's supposed to be always if we give a same time period, so it will be same. On
But
and off.
it's but
So
this
my
is,
drawing is not perfect.
no. I'm not saying
So it will be the same.
I'm the question because it's the we do not get the angle in
So this is in real time which signal is there, right?
yes.
But in practical it will
it's
take
yes.
like this.
So that's what
That's why
I have a
like
question.
this.
So the question is, if this is due to in practical, if this is delay, can both be different or similar?
Almost similar.
Okay.
So as we are taking the 50% here in the propagation delay from low to high, and here propagation delay from high to low. So average propagation delay, we should take always the average propagation delay. And the average propagation delay is our propagation delay of the circuit. Whenever we say the propagation delay, it will actually take the average of this one. So TP, but finally TP is equals to TPHL plus TPLH divided by 2. So this is our propagation delay of the IC. Now we can say the average propagation delay. We can say this is an average propagation delay. So in the waveform, we define the threshold voltage at 50%. Threshold voltage explain at which the voltage transition is happening. This threshold voltage is explaining at which voltage the transition is taking place. So for example, if we just consider during the 50% time, it will take at the 50% voltage, it will take the transition will take a start. And here also at 50% voltage, the transition will start. So here we are giving high, so you are getting low.
And that average is always positive, right?
Always positive. Okay. So TPLH, what we can say that the TPLH we say this TPHL and TP and H. The time required for the output to response, or to go from high to low. And TPLH means the time required for the output to go or response from low to high. Okay, so this is the propagation delay. And that's why we need to take average. So for example, if TPLH is 5 nanosecond and TPHL is 7 nanosecond, so we can say the propagation delay is 5 plus 7 divided by 2 is equals to 6 nanosecond. Very easy, simple. The second important parameters of the characteristics of the digital IC is called power dissipation. Power dissipation. The power dissipation is the amount of power dissipated in an IC. Of course, whenever we use the IC, we have to give some voltages, you have to connect it to the VCC and you have to connect it to the ground, then the current will pass through. And whenever there is a power inside the IC, it will dissipate some power in terms of heat. We can touch, whenever you touch the IC, you can some heat. That means there will always some power dissipation, and of course we have to know how much power dissipated will not destroy our IC. So power dissipation is equivalent to PD. We can express this power dissipation VCC times ICC average, the current in the IC. And this current in the IC is actually equals to ICC by ICCH plus ICCL divided by 2. What is ICCH? ICCH or ICH is the current when logic output is high, logic high at output. And ICCL is the logic low at the output. So logic low at the output and logic high at the output, because we have, when we give some pulse at the gate, the output will switch from high to low. We will always switch from high to low, and the amount of the supply current will always vary between ICCH and ICCL. The average power dissipation depends on the duty cycle of our input pulses. So usually we just consider the duty cycle is 50%. That means the same. So this is the duty cycle, right? So in total time scale, this is my on speed. So this is the duty cycle. So usually we take the 50% duty cycle. So the average power dissipation depends on the duty cycle and usually specified for a duty cycle of 50%. So when we get a pulse at the gate, the signal will come from on and off, right? High to low. And that's why the current will also consider from ICCL to ICCH. That's why we need to take the average of ICC. So average of ICC equals to ICCH plus ICCL divided by 2. ICCH, again I say the ICCH means the current IC when the output at high level or high level output power. Logic high at output. Logic high at output. And ICCL when current at this IC logic low at the output. So it will give you ICC. Then if you put the value here, it will give you the power dissipation of the IC. For the power dissipation for n number of ICs, n number of logic gates, because inside the IC we can have 4, 5, 6, 7, more than 8. So depending on the number of gates, this power dissipation will increase. So for n number of logic gates, the power dissipation will be VCC times ICC average divided by n. Why is n is the number of the logic gates. So this is the power dissipation for n number of logic gates IC. Okay. So just for example, if we have given the VCC equals to 5 volt, VCC equals to 5 volt, one example, simple, very simple example. The values are given. VCC equals to 5 volt is given. ICCH, that means current when the logic high, at that time current is 0.5 milliampere. When the current logic high, the current is 1 milliampere. And now we have to calculate the power dissipation. Calculate the power dissipation. So at first we need to calculate ICC average. So ICC average is equals to, we saw that ICCL plus ICCH divided by 2. So if you calculate those things, if you put the value here, it will give you 0.75 milliampere. And then PD is equals to VCC times ICC. VCC is 5 volt, 0.7 milliampere. It will give you 3.75 milliwatt. So this is the power dissipation of that particular IC. Okay. So if I draw this one, what is ICC and ICCH, whenever the logic high and logic low, we can see like this. So for example, this is a 2-input NAND gate. So in a 2-input NAND gate, if you go, both input are low, output will be high, right? So this is the output high output. Can you see? Is it okay? Output high. So here we have these VCCs connected to here. VCC will get PD equals to VCC into ICC H. Right? ICC H. On the other hand, if we have the low input and then get when both input is high, output is low, then it is VCC, then it will give you ICC, and then it will give you ICC H. So here the power dissipation for this IC will be VCC times ICC. So we are using the IC, so we can give the NAND gate IC, we can give the both input high, both input low. So at that time we will get either high output or low output. So depending on the high output and low output, the power distribution will be different. Then we can calculate the total power dissipation, whatever the total power dissipation is. The third one is the figure of merit or the speed power product. The third characteristics of the digital IC. So this is the second characteristics, the power dissipation. The first one was we talked about, which was propagation delay. The first one was the propagation delay. The second one is the power dissipation. The third one is known as figure of merit. That means the product of these two, speed power product, or you call figure of merit, or you can call it speed power product. As I mentioned, that propagation delay defines the speed of your IC, right? The propagation delay defines the speed of your IC. So it is a product of the speed and power of the IC. So it's a just propagation delay times the power dissipation. So this is the figure of merit. So this FOM or figure of merit should be as low as possible. It should be as low as possible. What about the unit? So for the FOM, the unit will be, so for the propagation delay, the unit is in second, or you can convert in second, in nanosecond. So if you give me a second, and the power dissipation is what? So what is in joule per second, right? Joule per second. So if you multiply these two things, it will give you joule. So figure of merit unit is joule. The next important parameter, the most important parameters of this digital IC is known as fan out. Fan out. What is fan out? The definition of fan out is the fan out of a logic gate. The fan out of a logic gate is the maximum number of inputs of the same series in an IC family that can be connected to a gate's output and still maintain the output voltage levels within a specified limit. Okay. Again, I am repeating the fan out. The next topic is the fan out. The fan out of a logic gate is the maximum number of inputs that can be connected to a gate's output and still maintain the output voltage level within the specified limits. Or in simple, we can say that number of similar gates can be driven by a gate without impairing the normal operation of that given circuit is called fan out. So if I draw this circuit, then it will be clear to you. So this is one gate. Any gate, it can be AND gate, it can be NAND gate. So now with the figure you can match the definition. The fan out of a logic gate is the maximum number of inputs. How many inputs we can connect to the input or the output of this gate. So this one is known as driven gate, driver, and these gates are known as load gate. One is known as driver, another is known as load gate. Driving gate or load gate. Driving gate, D-R-I-V-I-N-G, driving gate, and this is unload gate. So as I mentioned, number of similar gates, because they mentioned that of the same series of in an IC family. So number of similar gates can be driven by a gate without impairing the normal operations of the given circuit is called fan out. Fan out should be as high as possible so that we can drive larger number of gates by a single gate. Fan out should be high as much as possible so that we can drive maximum number of gates by a single gate. Okay. They should be in the same logic family. Okay, they should be in the same logic family. So that means if we have this AND gate, then if we have an AND gate, so it will drive only AND gate. So this is the driving gate, and this is the load gate. So fan out should be as high as possible. Fan out should be as high as possible so that we can drive large number of gate by a single gate. It is based on the amount of current, but it is based. So how much maximum? What is the range? So it is based on the amount of the current provided the output of the given gate logic. It depends on how much current is giving. We are giving at the provided, we are giving or we are provided how much current to the output of this one. Okay, it will be clear to you more. So here we can say what is the fan out for this circuit? Fan out is 3. Here we are driving how many gates? 3.
3 gates.
So if this one fan out is 1. If we have this one fan out is 2. Okay. So fan out is a significant parameter for TTL. Since very high impedance are associated with CMOS circuits, the fan out is very high but depends on the frequency because of capacitive effects. So whenever we see in future, there are 2 different kind of technology we use to design this circuit. One is the CMOS technology, one is the TTL based circuit. In case of CMOS based circuit, they have some frequency dependency. Because in the CMOS capacitor, there is CMOS oxide capacitors are involved. So that's why it is different between 2 TTL technology and the CMOS technology. They have some different, little bit different fan out. So fan out is a significant parameter for TTL. Since very high impedance are associated with CMOS circuits, the fan out is very high, but depends on the frequency because of capacitive effects. So we can write down the equation for fan out in terms of load, in terms of unit load or load, fan out for logic high and fan out for logic low. Fan out for logic high. What is this one? Fan out for logic high. Fan out for logic high means, so this is your AND gate, driving AND gate. Then it is creating some high. So when both input is low, high, output is high, right? When output is high, because this is an AND gate, when both input is high, output is high. And that means it is creating high output volt current, IOH. And this IOH is actually giving to fed some other input, right? Other input of the 2 input diode, sorry, 2 input AND gate, I'm sorry, 2 input AND gate. That means this is input high. So high output current will fed to high input current. So we can say fan out for logic high is equals to fan out is equals to I output high max by I input. Similarly, fan out for logic low. So that means whenever it will low output, IOL output low, so it will get input low. Okay. So I output low by, so fan out for logic, fan out for logic low, we can write down fan out equals to I output L raised by I input L. Okay. So in case of low state, for example, one example, in case of low state, that means for logic low, if IOL is given equals to 16 milliampere and IIL is given 1.6 milliampere, we can say the low state fan out is how much? So low state fan out is equals to IOL by IL. So IOL is 16 milliampere by 1.6 milliampere.
10.
So 10 milliampere. Sorry, 10. So that means it can drive maximum 10 amperes. It can drive maximum 10 amperes.
So 10 AND gates means it's a 10 ratio. The ratio we are.
So that means this is your AND gate,
Yes.
and it can have maximum 16 milliampere current. And to drive one input to input AND gate, it requires 1.6 milliampere. So that means with one AND gate, you can give input, drive 10 AND gates.
10 AND gates. That means 1 is equal to 10.
1 is to 10.
1 is to
Maximum.
10. The ratio.
Yeah, that's it. For a standard TTL gate, for example, is given for a standard TTL gate, IOH equals to, for a standard TTL, IOH output current maximum is 400 microampere, and to drive a current, to drive a AND gate, input IH is given 40 microampere. So fan out, high step fan out will be again 10. That means we can add 10 logic gates at the output of the driving gate. So a fan out will tell you how much gate you can add or how much gate you can drive by using the first driving gate or the driving gate.
Is it not like for every, for each individual AND gate? For example, if you take an AND gate, the driving and the current it can take is not same for all the AND gates?
Yeah.
Then how one single AND gate can drive multiple AND gates if it is same?
So this is how, for example, here we have the VCC. That we connected to here, right? So this is the power dissipation. So we'll see more whenever we calculate how it will control, how it depends on, then it depends on some called noise margin, because we need to consider logic 0 for certain voltage, logic 1 for certain voltage. If you keep increasing your gate, then the voltage drop will change, then it will reduce your margin. But here, as you mentioned, so this is the PCA, so we can consider how much current is here, right? The maximum it can current load. But to input and output, there is some difference. For the noise margin, we have input voltage level, we consider logic 0. So for example, this is the range, and this is the range. So this is for logic 1, this is for logic 0. Okay? So you consider from 0 to 1 volt, whatever it is 0 to 1 volt, if you apply, it will consider as logic 0. Then from 3 to 5, if the voltage, input voltage is from 3 to 5, we consider it logic 1. If anything from, for example, you give 1.1 volt, it will either not 0 nor 1. This is undefined. So for example, this is in input side. So input side, minimum voltage required for logic 1 is 1 volt, right? Minimum 1 volt. And if you want to give for logic 1, maximum required is 1 volt, here minimum required is 3 volt. So here, we already defined, for example, when this one, then we get some VOH, output voltage high, because it is high now. So when output voltage is high, then it will be some threshold voltage, minimum voltage required. So if you drive more than that current, then this range will reduce. So depending on that. So there is a difference. We consider the input voltage and output voltage. We will separate noise margin for input and output. And then depending on that, so it's still not like the input may be required 3.8 volt, but output may be required less than that. Okay. Then another term is that is very simple one is called fan in. Fan in means how many number of inputs of the NAND gate. We call it 2 inputs NAND gate, 3 inputs NAND gate, 4 inputs NAND gate. So if 2 inputs NAND gate means 2 fan in. Fan in is 2. 3 input NAND gates means fan in is 3. So very simple. So if I go for continue the fan out, so when the output of logic gate, is connected to one or more inputs of the other gates, a load on the driving gate is created. We can say, right? When the output of one logic gate is connected to one or more input of the logic gates, then some load will create here, some load will be created here. Okay. So there is a limit as the load is increasing. So there is a limit to the number of load gates inputs to a given gate can drive. So whenever you are increasing the gate, that means the current is also increasing, right? The current is increasing. So here this is I. So here this is I1. Here this is I2. Here this is IN. So current is increasing. So when the current is increasing, that means voltage drop here is increasing of the driving gate. So that's how we can control, how we can fix how many gates it can drive. I think you got your question. Yes. Okay. So we can say when the output of the logic gate is connected to one or more inputs of the another logic gates, a load on the driving gate. This is the driving gate. So these are my driving gate, and these are my load gate. The load on the driving gate will keep increasing. So there is a limit to the number of load gate inputs that a gate can drive. So as I mentioned, there are two different technologies. One is called CMOS technology, another is non-TTL technology. At first, try to understand this fan-out for the CMOS loading or CMOS technology. It is known as CMOS loading.
They use the same concept, like?
Yeah. CMOS loading. So we are still talking about the fan-out, but the fan-out for CMOS loading. Because what is fan-out? We are connecting the output of one gate to one or more of the another input gates. So whenever you connect the other inputs to the output of the first AND gate, that means loading is created. So that's why it is known as loading. So at first we are talking about this CMOS loading. Loading in CMOS differs from that in TTL because the transistor used in CMOS logic present a predominantly capacitive load. In case of CMOS, we have a predominantly capacitive load. In the CMOS, we will see there is some capacitors will be formed. That's why they are different. So loading in CMOS differs from TTL because in CMOS they have predominantly capacitive load. Predominantly capacitive load. What is this one? Okay, let me draw this here. If I draw, can you see here? So So we just with one gate, we are not giving so many gates here. Just try to understand with one gate here. So this is my driving gate. This is my load gate. Okay? So this is the 5 volt we are giving here. So 5 volt, this is the internal resistance. Here in the driving gate we have some capacitance. So whenever it is high, that means this current will charge the capacitor. It will charge the capacitor. Okay? In the CMOS, why it is important? Because it's different from the TTL, it has predominantly capacitive load. That means the load you are connecting, this is the load gate. The load you are connecting, it has some capacitive value. So whenever they are high, that means the capacitor is charging. Whenever it will be low, what will happen? Whenever it will be low, if I draw here, whenever it is low, that means at that time it is discharging. At that time it is charging. So it is I discharge. Okay, so in this case the limitation, what is the limitation? The limitation are charging and discharging time associated with the output resistance. So what is the charging and discharging time? RC, right? Tau value. So what is the RC? So the driving gate resistance to the load of the capacitance. So we have RC. So it is related with this RC time. So in this case, the limitations are the charging and discharging times associated with the output resistance of the driving gate and the input capacitance of the loading gate. So when the output of the driving gate is high, the input capacitance of the load gate is charging. Right? When the output is high, the input capacitance of this load gate is charging through this input resistance. When the output is low, then this load capacitance is discharging through this load resistance. So when more load gates are applied, so here we just draw only one gate, right? So if we have more gate, charging and discharging time will increase, of course, because the capacitors are connected in parallel, right? All the capacitors are connected in parallel. So this increase in capacitance increase the charging and discharging time. So this reducing the frequency at which the gate can operate. So if the charging time increases, the frequency of operation will decrease. Okay.
I have a question.
Yes, sir.
That is ground, right?
Yeah.
This is ground and that is also ground?
Yeah. So this is the path. This is a simple path, right?
Okay.
You have to complete the circuit. That's it. So whenever you have an IC, for example, we put into a breadboard, right? In the breadboard, we have some pin number. In the pin number, we put some, what you can say, VCC, and another pin is ground, right? Internally, they have that ground point. But in the IC, for example, there are 4 AND gates. So one will be the driving and 3 will be the load gate, like this. Okay?
Because so I was thinking, it's charging, right? It shouldn't be connected with the VCC to get the charge, and to discharge, that should be ground. That should be connected with the ground. That makes sense.
So no. So it does means when you give the input high. So logic high means what? As I mentioned,
5 volt.
logic high means 1, right? Logic 1 means either you are giving 3. It depends, because in CMOS I will show you. In CMOS they have different, in TTL they have different. In TTL they have 5 volt TTL. In CMOS they have different level. 3.3, 2.3, I show you. So if you want to give logic high, you have to give either 3 to 5 volt. That means you connect it to the VCC. So whenever you are connected to logic 0, what does you will connect? You connect to the ground.
Yes.
This is the ground.
Yeah.
So at that time what will happen? The capacitor will now find a path to discharge his capacitor,
Okay.
the charges. It will just discharge to it. Right? Okay. So when more load gate inputs are added to the driving gate, the load capacitance or total capacitance increase between the input capacitance effectively connected in parallel. What about the TTL loading? On the other hand, in case of TTL loading, there is no predetermined dominant capacitance value. Sorry. In case of TTL, so this is about CMOS, okay? This is about the CMOS loading. Now I'm talking about the TTL loading. TTL loading. A TTL driving gate sources, okay. In the TTL driving load, if I draw the circuit first, just only one gate, one driving gate, one load gate. So here this is 5 volt. Then connect this one, and then so this is grounded. This is my load gate. This is my driving gate. Okay. So when it is high, so current is, so this is 5 volt. And this voltage is, you can call it IH. If I show another circuit here. In case of TTL loading, the TTL driving gate, this is my driver, right? TTL driving gate sources current to the load. That means it will act like a source of this load. You can say that in the TTL loading, the driving gate sources current to the load. Sources current to the load, gate input in the high state, and sinks current. It's sinking current. When it is low, I input low, it actually is sinking because this is my driver, this is my driving gate, this is my load gate. The load gate, from the load gate, when it is low, from the load gate is actually sinking the current. So here it is driving the current or source of the current for the load gate. Here it is sinking the current from the load gate. So we can say that a TTL driving gate sources current to the load gate input in the high state, and sink currents from the load gate in the low state. It will source current to the load in high state. It will sink current from the load from the low state. So when it will be in the low state, when it will be low, like this, 0, 1, 6, 0. So it will sink current from the load. If it is in high state, it will source current to the load. Okay? In case of CMOS, it was charging and discharging. So resistors are internal. We can see that some resistors here, they are internal resistors for input and output gate. So if you increase as number of load here, so if you increase the gate, if you keep increase the gate here, the current will increase, right? The current will increase. If the current will increase, the output voltage will increase. Okay. So as more load gates are connected, these are the load gates, right? These are my load gates. All are load gates, 1, 2, 3. So how many fan out? What is the fan out here? 3?
3.
The fan out is 3 here. Here, fan out is 1. Okay. So as more load gates are connected to the driver gate, the loading on the driving gate increases. As more load gates are connected to the driver, the load at the driving will increases. The total source current increases with each load gate input that is added. The total source current, this is known as source current, right? I'm calling it, this is the source current, and this is the sinking current. This is the source current, this is the sinking current. If you increase the number of loads here, the source current will increase. If you increase the load here, the sink current will also increase. Sink current will also increase, load current will also increase. Okay. As this current is increasing, the internal voltage drop will, what will happen? So here, this IIH is equal to what? For example, this is I input H, sorry, this is IOH, IIH, IIH. So summation, right? Entering current, leaving current. If you apply the KCL at the node, right? Same. So IIH or IOH equals to IIH plus IIH plus IIH. So if we complete, this is load 1, this is load 2, this is load 3. If you keep increasing your load, your current is increasing there. So if the current is increasing here, what will happen? The voltage drop will increase. The voltage drop will increase. So VOH will also increase. Okay? As this current is increasing, the internal voltage drop of the driving gate increases, causing the output voltage VOH decrease. So output voltage will decrease. Sorry, input voltage is increasing, then output voltage will decrease. Again, I'm repeating again. Maybe you will get confused. So this is the TTL loading. In the TTL loading, we have the driving gate, we have the load gate. In the CMOS also, we have driving gate, we have load gate. Okay. In the TTL, the driving gate will drive or will be the source of current for the load gate. So we call it source current. If you increase the number of the load in the driving gate will increase. Here, this is when the output is low state. When the output is low state, that means the sinking, it is like a sinking of the driving gate. Like now its current is coming back, it's sinking the current. So if you keep increasing the load here also, the sinking current will keep also increase. Is it okay? Now, in both cases, the current is increasing in the driving side. If the driving side increases, then the voltage drop will increase. If the voltage drop increases here, then driving output voltage will decrease. Output voltage will decrease. If this output voltage decrease in case of source and sink. So one is the source. So my driving gate can be a source or can be a sink, right? My driving gate can be a source or it can be a sink. In a high state, it will act like a source. In the low state, it will actually sink the current. So if an excessive number of loaded, what will happen now? What is the problem? If we keep increasing, so you are giving this one, if you keep increasing, your load, number of load gate inputs are connected, so VOH will keep to drop. When VOH will keep to drop, and the high level noise margin will reduce. Now I will show you what is high margin, high voltage noise margin and low voltage noise margin. That noise margin will reduce, will become shading. So here power dissipation will also increase. Another problem, so two problems, or the two range, we cannot keep increasing our load gate until after beyond certain limit. Because if you keep increasing this one, what will happen? The first thing, your high level noise margin will reduce. First thing. And the second thing, if you keep increasing your current, that means power dissipation will also keep increasing. If the power dissipation increases, then it will become more heat and heat. Okay? So PD equals to, you already look at, right? VCC times ICC average. So ICC average means what? ICCF plus ICH. So if it is increases, power dissipation will increase, so heat will increase. So the total sink current also increase with each load current input. So if we increase the sink current, if I draw this one, so this is my sink current, this is sinking. So we can draw like this. Five volt. So it is IIL, 2, IIL1, IIL, N. So at the lowest state, you can see the current will go here, will go here, will go here. So this is my total current, total sink current. Right? So this is my total sink current. Everything is connected here. If you think this is a node, so this is my entering current, this is my leaving current. So this one equals to this one plus this one plus this one. So current, in both cases current is increasing, right? In both cases current is increasing. Here current is increasing. So here also, look at here. IIH. So this is total. So I input high, IIH, 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 input current high, input current high. So if you think this is the node, this is the leaving current, entering current, this is the leaving current. So everything is, so this is the driver, this is the load, this is the load, this is the driver. At lowest state, it's sink. At highest state, it's as a source. In both cases, the current is increasing. So when the current is increasing, the voltage drop will decrease. Output voltage of will decrease. Output high voltage drop will decrease. And here, the output low voltage will increase. So VOL, output low, will keep increasing. So if we keep increasing the number of load, after a certain point, it will exceed the VOL max and the low level noise margin will also reduce. So in TTL, the current sinking capability is the limiting factor. In the TTL, the current sinking capability is the limiting factor for determining the fat loss. Now, what is this margin? What is this VOH and VOL? Before going to this VOH and VOL, as I mentioned, there are supply voltage. We need to apply the supply voltage. So, voltage and current parameter for the CMOS and TTL. So, in every gate, we have input side and output side. So if this is my input side, sorry, this is my output side. If I draw the input side here, this is logic 0. This is logic 1. This is my voltage. To represent any signal as 0, we have to have some voltage range from CMOS, it is from 0 to 0.5. So what does it mean? I'm sorry, you cannot see. So if we want to give 0.6 volt, it will not consider as logic 0. So anything, any input, any output voltage which is in between 0 to 0.5 volt will be considered as logic 0. And here, this is 3 volt and this is 5 volt. So that means this is the output voltage and this is the maximum output voltage. VOH max. Right? So maximum until 0.5 volt, it will consider at logic 0. If your output voltage, whenever we have some output voltage here, VOH, right? We give it some VOH here, right? As I mentioned, VOH here. So we are trying to drive another gate here. So it will give you some voltage, output voltage from this one. So if this output voltage in between from 0 to 5, it will give logic 0. If it is in between, so that means VO max should be maximum 0.5. If anything more than 0.5, it will not consider as a logic 0. So this is the maximum to represent logic 0. On the other hand, for logic 1,
So is it not VOL instead of VOH? Because it's output low,
oh yeah, sorry,
but it's still max, right?
thank you, yeah. VOL, output low, yes. And here this is the minimum voltage, to represent logic 1. So if anything less than 3 volt at the output side, it will not consider as logic 1. So this is the minimum. And this is VOH. And here this is undefined. So if anything in between here, so this is for a band gap, for guard band, so that we cannot get confused. So anything between 0 to 0.5, it will consider as logic 0 at the output side. Anything in between 3 to 5 volt, it will consider as logic 1 at the output. So this is the minimum VOH, this is the maximum. Okay. On the input side, if I draw this one, in the input side, it is from 0 to 1 volt and 2 to 5 volt. This is logic 1, this is logic 0. This is undefined. So here it will be input low, VIL, input low, and this is VIH, input high. So similarly, from at the input side, so this is my input. So this is VOH, output of this gate. And this is input of this gate, input high. So there will be some noise merging. Okay, so that means to get the logic high, there will be some minimum input voltage, that is from 2 volt to 5 volt. If anything less than 2 volt, it will not consider as logic 1. So this is input high, minimum. Input high, minimum. Same way, to consider as a logic 0, at the input side, it has to have some maximum value. Maximum until 1 volt, it will consider as logic 0. If anything more than that, it will not consider logic 1 or logic 0. So whenever we give this signal, for example VOH from here, if the noise is added with our signal, and if it is goes beyond this 2 volt, then though we are giving logic 1, it will not consider as logic 1. Due to the noise, my signal level was 3 volt, but here to consider as logic 1 at the input side, it requires minimum 2 volt. Though we are generating 3 volt here, because our logic high output is 3 volt, but for the noise, maybe it drops to 1.9 volt. So that it will not consider as logic 1. So this gap is known as noise margin. This gap is known as noise margin, and this is known as high state noise margin. High state noise margin. What is high state noise margin? The highest state noise margin is VOH minimum minus VIH minimum. VOH minimum minus VIH minimum. As we are trying to get this noise margin of the logic high, that's why it is known as high state noise margin. Yes, sir.
Is it ever reversed with VIH being larger than VOH?
No, we have to go. No, VOH will be higher. VOH minus VIH. Yeah. So on the other hand, for the lowest state noise margin, the lowest state noise margin will be low state noise margin will be the difference between these two. So input high minimum minus output high. Input high minimum minus output high. Sorry, input low minimum output low. VI low maximum minus VOL maximum. Because this is the maximum level. This is the maximum level. So VIL maximum VOL. So as I mentioned, what will happen as in if an excessive number of gates of your load gates are inputted, VOH drops below VOH mean. VOH drops below VOH mean. If you keep increasing your number of gates, okay, the fan out. So the fan out is 10. Now you have to make, that means you can drive 10 gates. But if you add 12 gates, what will happen? The VOH will drop. So if the VOH will drop, then it will not generate proper output. So that whenever you want to drive any load, you are giving logic 1, but it will not get logic 1 here. Okay? So VOH will drop or the noise margin will reduce. On the other hand, if you increase this, when the sinking at the lowest state, when you increase the load, the VOL will drop. The VOL will drop. VOL maximum will drop. This range will drop. So here, what is the range? For example, here for this, it's not mandatory, it will be always the same. But in this example, we found that VOH was, we call 3 volt, and here it is 2 volt. The noise margin is 1 volt, right? Here we consider this is 3 volt, here we consider this 2 volt. So noise margin is, highest noise margin is 1 volt. And here, that means it can hold, or the noise margin, it can consider at logic 1 and logic 0 in between 1 volt. And here the noise margin, how much? It is 0.5 and 1. So 0.5 only. 1 volt minus 0.5 is to 0.5. So this is the noise margin. So there are 4 important parameters. One is VOH, minimum output voltage for logic 1. VOL, maximum output voltage for logic 0. VIH, minimum input voltage for logic 1. VIL, maximum input voltage for logic 0. So this is the 4 important parameters we have: VOH, VOL, VIH, VIL. And we have two noise margin. One is the highest state noise margin, and another is the lowest state noise margin. Highest state noise margin difference between these two, VOH minus VIH. And here noise state means VIL minus VOL. Here input minus output, here output minus input. So as I mentioned, the DC supply voltage are different from CMOS and TTL. In case of TTL, we use 5 volt DC supply. Typically we use 5 volt DC supply. In case of CMOS, complementary MOS device, it can be 5 volt, it can be 3.3 volt, it can be 2.5 volt, and even 1.8 volt. So there are some variation. Okay. So if I have few moments, so I just drop few things here. So depending on your supply voltage, the range will also change. So for example, so far I draw, so if I draw for the CMOS with 5 volt, then the range of input and output, it is 3.5 to 5 volt for logic 1. This is my input side. And here it is 0 to 1.5 volt for logic 0. So anything until 1.5 volt we'll consider at logic 0. This is input side. Anything above 3.5 volt we'll consider as logic 1. So this is the minimum voltage for logic high, and this is the maximum voltage for logic low input. Okay. So this is V I L and this is V I H, because we are talking about input. So this is high, this is low, and this is the minimum, and this one is maximum. So this is for CMOS with 5 volt. And what about the output side? In the CMOS, this is a standard one we have to maintain. So here a huge range. So this is VOH, output high, because this is my output side. This is logic 1 and this is logic 0. And here it is only 0.0233 volt. So this is VOL, output low, max, and this is V input high. So we can see a huge margin. How much margin? A huge margin. It's a 3.52. So this is only 4.4 volt to 5 volt. So margin is very high. 4.4 minus 3.5. Right? Okay. In case of 3.3 volt of the CMOS, this one from 2 to 3.3 volt. So if it is 3.3 volt CMOS, so it is from 2 volt to 3.3 volt, and here it is 0.0 to 0.8 volt. So in for the input side. In the output side, it is from 2.4 to 3.3, and here it is 0 to 0.4 only. So these are the things. So if I have a circuit like this, so for example, if we have a circuit like this, and here we're driving this gate, this is the load gate. So we just mentioned VOH, mean here 4.4 volt, okay, 4.4 volt. And here we are giving, this is the noise margin, VIH is equals to 3.5 volt. So VH mean and VH mean. And this is my noise margin, right? This is my noise margin. So the voltage on this line will never be less than 4.4 volt, unless noise will introduce, you can see. So this is the noise margin, 4.4 to 3.5. So we'll continue from here. We'll talk a little bit about the noise margin, that will move forward for the RTL and DTL circuit. So these are the few important characteristics of the parameters of the digital IC, the propagation delay, then the power dissipation, the figure of merit, that means the power product, and most importantly the fan out. The fan out will decide how many gates you can drive with your single gate. And depending on that, it depends on two things: the power dissipation will increase, as well as the noise margin will reduce. Because we have some standard value, for example, these are some standard value. So if you want to maintain this standard noise margin, this gap and this gap, we have to have limitation, how many gates we can add. So this can tell us by the fan out calculation. And then fan in is just simple, the number of gates, how many 2 inputs AND gate or 3 inputs AND gate, the number of inputs decide the fan in, fan out and fan in. And finally, we discuss about the noise margin. So we have two noise margin: high state noise margin and the low state noise margin. High state noise margin related to the logic 1 between output high to input high, and the low state noise margin, the difference between the logic low state between input low minus output low. So I will upload these handouts, don't worry, and also you can find all those information in the reference book. So there are 2 chapters, maybe I forgot the chapters, but you can see that one is related to the TTL, CTL, it is around chapter 11 or 12, and another information you get at the 2nd chapter. So I will mention this. So please go through the reference book, and also you can go through this my handouts. Thank you so much. Have a nice weekend. Oh, I forgot this.